thank you first to the organizers for the invitation to this wonderful place and to speak here. So today I'm going to discuss a generalization of the DHR theorem to higher form symmetries. This talk will be based on a work to appear in collaboration with Horacio Cassini. We hope it will appear this year. So the motivations are very simple. Let me start with that. So on one hand, we have recent works by Choi, Lam, Zhao, and in 2022, and Cordova and Omori in 2022. They appear quite at the same time. That claim non-invertible symmetries exist in the greater than 2 space-time dimensions. Now, these works have raised a great deal of attention in the string theory and condensed matter community. Of course, we knew that this type of symmetries existed in the equal to 2 since very long time, but they were not known in higher dimensions, and this explains the burst in activity. On the other hand, we have the DHR theorem, which, of course, it's a complex theorem, but let me, for the purpose of this talk and for the motivations of this work, let me put it in modern, maybe modern terms. It says that zero form symmetries in the greater than 2 are groups. So there is an obvious tension between these two results, or these two lines of work. This is barely discussed in the literature, and let me say that for the specific cases that they were discussed in these two papers, in an article with Valentin Benedetti and with Horacio Cassini, we saw that these supposedly non-invertible symmetries were secretly, well, not so secretly, but they were invertible symmetries. So they were coming from groups, but this motivated us to clarify a little bit the origin of the DHR theorem, maybe to simplify it for the high energy community, and also to generalize it to all kind of symmetries, all the type of symmetries that have appeared in the literature. And the final motivation comes maybe is phenomenological. So we know that confinement order parameters such as the Wilson loop or the Toff loop are labeled by what is called the enality, which is a fancy name to say elements or representations of the center of the gauge group, which typically is, for example, the UN. Okay. So typically is an abelian group. In any case, in all cases, is abelian. So in the spirit of Toplicher and Roberts, we could ask, well, why this is the case, why, if there is a reason, why confinement order parameters are labeled by abelian groups. No? So the motivations are quite simple, but are there questions about the motivation? Okay, so
yeah, maybe. Yeah. So when you say the zero form symmetries in D greater than 2 are groups, I mean, yeah. So what's the claim? Is the claim that somehow if you extend the Hilbert space, that things that were non-invertible on some smaller Hilbert space become invertible on the larger one?
Well, that's a little bit the discussion. It's an open discussion. What is happening? But this is the claim. The claim is that at the end of the day, in the complete theory, in the theory that well, we will talk about that later. But there is, so the difference is that let me say it another way. In 2 dimensions, you cannot erase non-invertibility by going to a larger net. No, the claim is that in D greater than 2, this will always be possible.
So D here is space-time dimension, is that right?
Yeah, space-time dimensions, yeah, this is a space-time dimension.
I mean, even in 2D you could, right? Because you can take the Kramers-Wanier duality line and, okay, it sets some things to 0. If you include the twisted Hilbert space, then it could become larger on the sort of the Hilbert space.
I'm going to let me continue. For example, the dimensions. I mean, this implies. Let me say it in another way. This implies that the dimensions are integers, the dimensions of the sectors. Okay, this claim, because the dimensions of the representations of the group are always integers, and here you have in d equal to 2 at least you have dimensions that are not integers. So that's a difference, for example. Actually, in the examples that have been constructed in the literature, in d greater than 2, dimensions are always integers. So this suggests that something is going on, that the analysis is not complete.
In d greater than 2, the dimension is not well defined, I would say, but okay, we can discuss.
No, it's going to be well defined. I'm going to. We can talk about that during the talk.
So just a question on language. In symmetry, I feel a symmetry of the extension.
Yes,
I don't see the symmetry if you start from the.
I'm going. Okay. Yeah. Let me continue. So, actually, so let me explain the plan. The first part is going to be a review of, let's say, 3 phases of symmetry, and it's particularly to answer your question. There are many approaches, but well, there are 3, and sometimes it is said that the difference in these questions lies in the difference of approaches. But I'm going to argue that well, they are all different phases of the same coin. Okay? And this will also allow me to describe in detail what I'm going to classify. Okay. Then I'm going to comment on assumptions, mainly to expand on one of them that we call, we find quite interesting and not consider in detail, which is called logical transportability. And then I will go to the main results of the work. One is, let me call it, let me take a license here. It's not really a new derivation of the DHR, but you will see that it's a complementary new derivation of the DHR in the speed. Okay. In the derivation of the DHR. This is not completely needed for our results, but it will clarify and actually I think it contributes very much to this, to alleviate this tension. Okay. And the 5th is just the generalization. So, what are these? Just let me discuss. This is symmetry. Well, as a disclaimer, I won't talk about topological field theory, so I will always talk about local quantum field theories. So what I'm going to say applies to local quantum field theories, and probably there are things that will apply to topological field theories and some things not. So take that into account.
How do you separate the two, just out of curiosity? I mean,
well, I will. You will see. I will tell.
Topological sectors, right? Even in
no. But you can see you can see them in the local quantum field theory. Yeah, I'm going to. Yeah. Okay, so the first is the standard. I mean, sorry, maybe some people will be offended by that. But I think it's the standard is nowadays, at least in the high energy string theory community and the condensed matter community, this approach, at least nowadays, this approach focus on the topological maps. These are some codimension. So this is some map M. Defined on a codimension P hypersurface. It will act on operators that can be linked to them. And the defining property of these maps is that they can be freely moved. So freely move over space-time. They commute with the stress tensor. So they are transparent to the stress tensor. If there is, you can, for the purpose of this talk, you can assume that we have a local stress tensor. So this is the justify the name topological. Since it's topological, we can so to define the action on an operator, we can just collapse the map toward the operator, and this will give me the transform operator, whatever it is. Okay. Now these maps have some labels, and they can be fused. So this is a fusion category, which we have heard about. This is a fusion category, which we have heard about quite a lot these days. And here is where the local quantum field theory appears. And this is something that is not noticed in the literature, in the standard literature. So these maps can be generated from the local quantum field theory via the action of, let me call it some operators, let me call them T for the purpose of this talk, via commutation relation with the algebra. So if you have, here you will have an algebra in a local quantum field theory, a non-trivial algebra, and it will be the field algebra. So in the standard approach, you are always thinking that you are in the field algebra. Okay.
What is the map from where to where?
Is the map from the field algebra, is a local map from the field algebra to the field algebra that is local.
Okay.
Okay. I'm just saying that there are operators that that define the by via commutation relation. So so let me put it. So say an intertwiner for map A will have this commutation relation. So there will be operators, local operators in the theory. I mean, local, not local in the sense of point-like, but operators that are that can be localized in a region that act as intertwiners of the category of topological maps. This is not the same. This doesn't happen in topological field theories. Let me put you an example. For example, for a standard internal symmetries. So for standard internal symmetries, this is codimension 1, and then I can take, for example, my TA. I can take it to be for a group like symmetry. I can take it to be the global symmetry generator. This is an operator acting on the Hilbert space, and when acting on the local algebras of the, let's say, of the field algebras, it generates this topological map, obviously, where this topological maps is by construction UG minus 1. Okay, see. But the point is that for local algebras, you cannot. There are many choices of this. So, for example, you could take a symmetry generator that is more localized, so a twist, what is called a twist, that is localized in a certain region. Okay. Okay, this for that. Then we have the algebraic approach. Or let me call it DHR. This focus on DHR sectors. These are maps. So these are which are let's see, rho R. We call this region R, and then basically these are endomorphisms of the algebra of R that leaves the algebra that are local to some extent. So they are localized and they leave the outside invariant. Okay, so they are localized and transportable. So this is the defining. So if this is topological, these are localized and transportable, which means that well, that they have a localization region. They act as the identity outside the region, but the localization region can be moved by operators in the quantum field theory. They again have some labels, and they again can fuse. And they form a C-star fusion category. And so here is the point. Here is where you see that the two things are very much dual to each other. So if in the category of topological operators, the intertwiners that generate the topological maps are the symmetry generators, in the category of in the DHR category, the intertwiners are the charges. Okay, so if I have I have some charge, and by commutation relation with some operator, it will generate the endomorphism. Okay.
So just the notation. So
Yeah.
F on the left hand side is what? The little.
No, F. I'm just saying this is a question by Sebastian. So this approach is F. Well, yeah, this is a small F. Yeah, yeah.
Oh.
Yeah, this is a small F. Yeah,
Field.
yeah.
Yeah.
I just want to say that this acts on the field algebra.
Oh, it's a field.
Field algebra, and here it's on the observable algebra. But in this very precise way, they are dual to each other.
Yeah.
Okay. This we are going to explain.
The charge and the field.
The charge belong to the field algebra. Yeah, of course. Yeah. From our perspective, these intertwiners also you can think. Well, let me continue. Yeah. So the last approach is we call it hard duality violating approach. We have been developing it for the past 5 years. So we have many motivations for this, but one of the motivations was to unify these two approaches and also to generalize this, to generalize symmetries. And I mean, at the time, now we see that, well, it's a matter of taste, but at the time we find more convenient to leave the maps, I mean, the idea of maps behind, both topological and endomorphisms, and to focus, so this approach focus on the algebra of the T's and the phi's. Okay. So one convenient thing of this is that these are the actual observables of the theory. So these are actual observables. These are the things that you can measure in experiments. And actually, these size are the parameters, and these T's are the disorder parameters. Okay. Now, one we call it hard duality violation approach because basically the fundamental starting observation is that these guys always, so whenever you have some order or some disorder parameter, it will always violate duality in certain appropriate region. Okay. This has a really well. If you have one, yeah, I challenge you to look from this perspective, and you will see that all the time it is exactly this way, and it has a lot of consequence. For example, the first consequence is that order cannot exist without disorder, and which is quite nice. So this cannot exist without this, for example. And also a nice thing about this formulation is that we can frame the DHR theorem, which is basically a classification result on the category of DHR sectors, into the classification of well, the violation of duality. We are going to discuss that in a moment. But let me say that in that frame, now we can generalize it to any kind of region. So we can now define what do we mean by a generalization of the DHR to higher form symmetries, and a classification of symmetries in general dimensions by a classification of hard duality violations for general regions. Okay, and that's what we are going to do today. Okay. Okay.
These are zero forms.
No, zero form. So I'm going to explain what it zero form. Zero form will correspond to hard duality violations in balls or in two balls.
Okay. So
Okay. But now you can consider, yeah, exactly. So for example, we can consider pure gauge theories, and pure gauge theories will have Wilson and Toff loops that violate duality in rings. Okay, and what we want to classify is the possible hard duality violations in rings, and this will classify confinement order parameters. Okay, so that's the generalization.
just because you wrote zero.
Sorry, where that?
Wrote zero in.
No, the DHR. So the DHR in principle, the DHR, really the DHR, the original DHR framework only considers zero form symmetries. Okay, so our motivation, as I was saying, to develop this was to extend the tools of these people, so that we can also consider higher form symmetries. And the way we found now there are, well, we understand better, but in the time, one way that is very precise and correct is to consider hard duality violations for general regions. Okay, so having that in mind, we just comment a little bit on assumptions. So we want to so as I said, we are seeking to understand things like this. So hard duality violations, no? But for general regions. So let me kind of take some assumptions that, well, with that objective in mind. The assumptions that we take, let me say that they are not, we didn't intend to be optimal. We are just taking the assumptions that we find natural, and that from which from which our results will follow in a most natural way. Let me say it equivalently, we are trying to make our lives as easy as possible, and to make the physics most transparent. So we live for a future work, maybe having a more optimized set of actions. But the first is that the regions that is about the regions we are going to consider. We are going to consider regular opens. This means equal to the interior of the closure. We are going to assume that there is an algebra for such a region that is non-trivial. So this rules out topological quantum field theories, for example. We are going to assume that we are going to focus on flat space. So our regions are always subsets of flat space. And well, the algebra of the full flat space is irreducible. Acts irreducible. Okay, so it's the full.
One question.
Yeah.
So okay, so you're ruling out topological field theories. If I couple a topological field theory to some other theory, like I have some gauge theory and I couple a topological field theory.
The point is that is a misunderstanding in the standard literature. It understands the symmetries in quantum field theory, generalized symmetries in quantum field theory by a coupling a topology, but you don't need to do that. The symmetry is already in the local algebras. This is what we have been working on. We can discuss. I don't have time to, but you don't need to do that.
Right, you could gauge. You could start with some topological field theory. Start with something which satisfies your axioms and gauge it.
Let me postpone. We can discuss that. I don't have time to discuss that, but it's all the information, because you see in the local quantum field theory, all these maps that so what you call topological field theory, the coupling of topological field theory to quantum field theory, is that you have these topological maps, which is a topological quantum field theory, okay, and you couple it to the local quantum field theory. But what I'm saying, I mean, the observation that you have to do is that the coupling is already on the local algebras, okay.
You can gauge symmetries, right?
Mm,
Gauge discrete.
Let me discuss that later. I mean, let me discuss. Yeah, we discuss. I mean, those things are yeah, we can discuss that later. But it's included. It's included secretly. Okay.
So as long as it's non-topological, then your claim is that it satisfies axiom 1.
No. I'm just classifying what is the class of theories I'm going to focus on. I'm just saying that this rules out topological field theories. I mean, that a topological field theory is not inside these axioms. What is inside these axioms, I don't know. But I'm just saying as a disclaimer. The second assumption is locality. Locality can be nicely framed exactly as saying that the algebra we associate to a region is included in the commutant of the algebra we associate to the complementary region. Let me just say that this locality condition suggests the definition of what we call the maximal algebra of the region, which is all the operators that commute with the complement. Okay, and this actually defines our object of study, which is the hat duality violation. We say that there is hat duality violation when this is not equal for some region. Okay. Then we assume a strong additivity. A strong additivity says that the union of algebras is equal to the algebra of the union. Basically, this is a condition. This condition, I mean, the non-trivial part is that if we have two regions whose closure touches, but they don't touch, the additive union of the algebras will not see that. So we'll basically fill this codimension 0 part. So this we have seen in various talks in the week that well, this is kind of a maybe a strong assumption in two-dimensional quantum field theory. We believe that this will not be the case in higher dimensions, which is the focus of our, but this is of course left to prove. But at least we don't know examples in higher dimensions that violate the strong additivity. Strong additivity implies is quite a nice property. It implies isotony, which says that if we have two regions included one in the other, the algebras are included, and also the maximal algebras are included. In conjunction with one, with the fact that they act irreducibly, it implies that the algebras of regions are factors. And also, if we take commutant, it says that if the union of algebras is the algebra of the union, the intersection of maximal algebras is the algebra of the intersection. Okay, and this in turn implies that this subfactor is irreducible. Okay. Well, then the fourth assumption is that the algebras are of type 3. In principle, this might not be necessary, but well, first probably is true, most probably, and second, it is quite convenient because it implies property B, which Borch's property, which is very convenient for studying symmetries, particularly. Then the next assumption is that the hat duality violated inclusion is of finite index. This is a generalization of the rationality condition in 2 dimensions. Again, this we don't believe it's necessary for our theorem, but of course it simplifies. For example, in the DHR case, they don't assume this. This is true for, let's say, for continuous group and finite groups. The theorem that we have proved for the moment is only true for finite groups. In principle, there is an extension to be done there. So, but we wanted to make it as, let's say, as simple as possible. And of course, finite index allowed to import subfactor theory, which was well, I don't know exactly the history, but there is a seminal paper by Roberto and Rere. In the case of finite index, we know that we have a conditional expectation from the maximal algebra to the algebra. We have a canonical endomorphism, which is basically this conjugation with the J operators of the two different algebras. We have the dual canonical endomorphisms, which is the restriction to the algebra, which can be decomposed into. So there is a lot of machinery that we can use, and the index is just the dimension of this canonical endomorphism. Okay. And then we have two other two other assumptions that are well known. One is the split, and another is essential duality. Which we can just frame it as saying that the dual net. So for balls, if I take the maximal algebra for balls, this is also a local net. Okay. Are there questions about these assumptions?
You need a vacuum vector or
Yes. For the purpose of this talk, assume whatever you feel comfortable with. I'm more focused on the physics and at least for confinement order parameters there is a vacuum, yeah. Okay.
This is for ball. Huh?
What? The essential duality is only for balls.
You are looking at time zero.
This is a discussion. The regions. Sorry. This D. Sorry. Maybe put it D and D equal to D plus 1, sorry. So the discussion is of the regions is at time zero. You can always think about causal completion of any region, okay? But the discussion is not really relativistic in nature. It's more topological in nature and just has the these are kind of standard in some way. Let me expand on some other assumption that we call topological transportability. Let me say that this assumption is implicitly assumed in all the approaches. So, for example, in the DHR there is a notion of transportability of the DHR sectors. Here also the notion of the fact that topological maps can be freely moved, but I think. So basically this assumption, these things that I'm going to comment is an axiomatization of those properties that basically allows full generalization and it's just a nice expansion on those properties, okay, which are implicitly assumed, but we don't really know what they are. So let me start by a definition. So we say that for two regions, if one is included in the other, we say that are transportable to each other if these both things happen, okay? So what are these conditions? So it says that so we have this situation. So we have a region R1 inside a region R2. In principle, they can be completely general. Then what we know for sure is that the difference between the two, so it's just, let me call it R, it is exactly the same as the difference between the complementary regions. So this would be R2 prime. This would be all this would be R1 prime. So what we are asking is that if we want to find the maximal algebra of R2, which is the big region, it is enough to take the maximal algebra of R1 and the algebra of R. So in other words, the non-local operators of R1 are also non-local operators in R2, and also not only are also, but are all the ones that we need. Okay, and the same for the complementary region. So this is of course a self-dual notion. It's transparently a self-dual notion. And but in what sense this is a notion of transportability? Well, in the article we prove a proposition that says that this property is equivalent to these three properties, and these three properties are equivalent to each other. So what are these three properties? The first is that the conditional expectation of the big region restricts well to the conditional expectation of the small region, and the same for the complement. And the conditional expectation of R1 prime restricts to R2 prime. This is also transparently self-dual. Okay. The next is something that let me put this. Sorry. the next two properties appear. I mean, it's the starting point. Well, the next property is the starting point of the article of Roberto and Reren, nets of subfactors. It says that so we keep this part, we keep the first part. So the condition expectation of R2 restricts to R1, but now we change the complement and say that and it exists a vector cyclic and separating for both maximal algebras and invariant under the big condition expectation. Okay. This is the starting point. So in a way, yeah, you are taking that as an axiom also. And in the article, they prove that this is equivalent to the fact that the canonical endomorphism of the small region extend to a canonical endomorphism of the large region, with the condition that the restriction on the algebra of R of the difference is the identity. Okay. And well, in our article, we prove that this basically these kind of definitions can be proven for any region. It's not about balls or about a particular net. So now we are okay with these preliminaries. Let me just make a further definition. So we say two regions.
It should be R2.
Well,
Third.
here.
Gamma R1 extends to gamma R2.
Two, yeah. Sorry. Yeah, correct. So now let me take another definition. We say that two regions are topological deformations if of each other if R is a ball or topologically a ball, and R1 and R2 have the same topology. So for example, I don't know, these are topological deform. Sorry.
What is the dimension of the space-time?
The dimension of space-time is greater than 2, whatever. Any and any region satisfy. Yeah. So we say so in that case we can now formulate the assumption in full generality. The assumption is that if we have an inclusion of regions R1 inside R2 which are topological deformations of each other, then these regions are transportable in the sense of all this. Okay, this is the assumption.
But the subfactor is A into A hat of the region.
Yes.
Okay, and you move the region.
And I move, yeah, so this is exactly what I'm doing here, no? So the subfactor is, for example, I have two regions, then I have two subfactors, no? I have AR1 included in a max of A1, and I have A of R2 included in A hat of R2. What this condition is saying is that the difference in, so the structure of, so yeah, let me say, so actually, there are 4 versions of transportability which are equivalent. The deepest one is this one, which was arrived at by Roberto. This is the deepest one because it says that the sector theory associated to these two inclusions is isomorphic. Okay. Okay.
The regions of the same type.
Topological deformation. So this is where the definition comes. We say that two regions, one included in the other, whose difference is a ball and has the same topology, they are transportable. But the definition could apply to other kind of things, because you could have a quantum field theory in which still it so happens that they are transportable for regions that are more general. Okay.
So the equivalence relation has the same topology. Is that the
Yeah. For example, you have a ring.
Yeah, it just says that it has the same topology.
Yeah.
Okay.
Yeah, basically it's the idea that you are moving the region.
Yeah.
It's just formulating that idea. You have a region and you just move the region.
Yeah.
So there is some kind of homotopy too with the same topology that
But you also deform the region.
you can deform it, but not topological.
But not topological.
But the difference being a ball means that they share one boundary, or they are like one bubble touching.
One ring, essentially. You have in mind. I think.
What?
You have in mind a ring.
Yes. Yeah.
But the difference is not a ball.
Yeah. Sorry. Now I'm maybe I confuse one or other assumptions. Let me say for the it just for example.
Maybe you can draw it.
Yeah, okay, I see your point. Okay, you say, for example, I have a ball here and another ball, and the difference is not a ball. Well, but it is a ball because Why? Because I can first transport it here. Now I have this, and now I transport it here. So I transported it. I do 2 transports. Okay. So yeah, you have to take care with this. You can my intermediate transports.
Okay, move it.
Yeah, you can move it. Okay. So yeah, this is, sorry, maybe this is not precisely formulated like that, but it is exactly. So basically we say that they are always, when I have a region and I put a single ball, and then these two regions have the same topology, and then it is transported. Okay, so there is another, I don't have time, there is another assumption that we find very natural, which, well, let me just comment it. We call it weak modularity. So in the talk, the next talk by Gandalf, he explained to us this logic of space-time that is like a Boolean algebra. And so in these algebras, in these logics, there is distributivity between unions and intersections, but not for the net of algebras. And the reason is exactly this high duality violations, okay? Well, this weak modularity is kind of a particular case where that we expect that happens. But I don't want to comment too much. We can comment later. Okay, so let me go to, what time is it? Let me go to the main results. So
Modularity in the sense of conformal field theory, or
no, weak modularity in the sense of volume. So modularity of the Boolean algebra is the fact that you have distributivity, of intersections and unions. Let me just write it. So basically you have this question. You have some algebra of region R1, and you have you united with the algebra of R2, and which is intersected with the algebra of R3. Okay, and you want to say if this distributes. Okay, it won't distribute in general. Okay, but there are cases where it distributes. For example, if R1 is included in R2 union R3, it distributes. And also, more importantly, if R2 is strictly included in R1, and also R1 is separated from and R2 is separated from R3 by a non-zero distance, then this is true. It distributes by the split property. You can prove it. Weak modularity is just taking that to be it's just saying, well, I can just join the regions and it won't happen anything. Okay, so maybe you have, for example, this situation. You have R2, you have R1, so R2 is really included in R1, and then you have R3 that makes something like this. I don't want to enter. Let me go to the results. Sorry, we can discuss later. Okay. Well, one thing that you can play with these assumptions is that, I don't know, for example, assumption 9, weak modularity plus strong additivity implies topological transportability. So in that sense, this kind of assumptions are nice. And also now with this kind of assumptions, the full difficult part of the article is to, whenever you have a net and maybe you go to another net, whether you can move all these assumptions from one net to the other. Okay, that is the. Okay, so before that, let me go to this new derivation of DHR. And for this, I want to describe first, an very insightful article by Yasu, Roberto, and Muger, which completed a program that was, I don't know, started or at least considered before in the case of loop algebras by Feng Shu. So this is in the context of 1 + 1 CFT, and the question is very simple. So basically, in the context of so you have a line, and you can consider the interesting region to consider is the union of two intervals. Okay. And you can ask exactly the question that they ask is exactly the one that we are asking, okay? But for this particular case, okay? And the answer they find is that this is controlled by the DHR category, okay? So I want to describe the main propositions, at least from our point of view. So the first is that if you have two, so if nu and sigma belong to the DHR category, then I can construct, I can localize nu in I1 and sigma in I2, and this is an irreducible DHR sector, I mean, of this region. And then this belongs to the canonical endomorphism if and only if sigma equal to nu, and to the conjugate, and in this case, the multiplicity of appearance is equal to 1. Okay. Now, the intuition for this, for the proof of this is very simple. It's just that if this is the case, there is an operator that creates this from the vacuum. But if there is an operator that creates this from the vacuum, it's necessarily the case that this is the conjugate of the other. Now, the second is that if we have two nets in tensor product, then an irreducible endomorphism of the two nets of DHR is isomorphic to 1 in sigma 1 times to the tensor product of 1 of A1 and 1 of A2. This is very intuitive, so I don't need to explain the intuition because it's already intuitive, but it's quite subtle to prove it. But it is like that. The third is the most important theorem of the work, which is the fact that the canonical endomorphism is isomorphic to the sum over all DHR of sigma r bar, okay, which implies that the global index is the sum over all DHR of dr square, okay. And the final proposition I want to, which is also important, is whenever you have an inclusion of net in 1+1 dimensions, you have some index associated, some global index associated to this net, some global index associated to the other, and you have the relative index between the two nets. And there is a beautiful relation that says that mu A equal mu B. Okay. Well, sorry, maybe this is too fast, and maybe just the experts, the one that have thought about this will know. But well, one of the parts of the paper, we need to generalize this to higher dimensions. So with respect to using that assumptions, we can generalize this context. So now we have two balls in higher dimensions. So in quantum field theory, in D+1, and basically we don't claim originality here. It's an exercise just to prove that this it's okay. So the same question goes to the same answer. In fact, this is the same. This is the same. This is the same. But we needed this generalization for the next theorem. So it was just a hard exercise with no reward. But actually, there was a reward because here it's not the same. So here it changes, and it's mu A equal to mu B times only one I. Let me just give the intuition for this. So this mu is the index of A of R inside A R, but I can break this. This inclusion into a chain, and I can first include the A of R in B of R, this in B maximal of R, and this in A of R. Now, this in higher dimensions is still I square. This is by definition mu B, but here this inclusion changes because in 2 dimensions this is the same. This is isomorphic to, so the complement of two segments is 2 segments, but in higher, so it's disconnected. But in higher dimensions, the complement of 2 balls it's connected. Okay, so then you get only one I, and then you get this relation. And now comes the proof. So this is very important because now imagine that we take the let's say the perspective of the standard approach in which we are in a complete theory. So so the perspective of the DHR approach is we are in the theory of observables. Let me call it A, and we look for extensions. I could frame it in a different way, and I could say, well, I'm in the complete theory and I look for subfactors. Okay, it's dual. In that sense, it's not exactly the same, but at least from a physics perspective, it's the same classification. So I'm in a complete theory B, and I look for theory says that are and look for that relation. So then, if this is complete, this relation says that mu A equal to I, where this is I. But what is I? I is by definition some sum over some multiplicities of the dimensions. These multiplicities, the only thing that I know is that they are integers greater or equal than 0 and smaller or equal than the dimension. But now I can use this result. Okay, so this is also equal to mu a, which I proved that is sum over r squared. And this only can be possible if dr equals to nr, which you might find very natural, but this is not the case in 2 dimensions, for example. And in particular, it implies that dr belongs to the integers. And well, sorry, I don't have time to discuss, but this implies that the DHR endomorphisms are, I mean, Reren proved that this implies that the DHR endomorphisms are implementable by the Kunze symmetries. It implies that there is a Hopf algebra action, but now I can prove that that Hopf algebra action it's a group because I can construct explicitly the statistics operator. So this is another, so then the symmetry is a group. So only in higher dimensions, subfactors have to be given by groups. Following this. Okay, if you let me 5 minutes, I just finish with
A lot of questions.
Okay. So let me just describe the extension. I mean, I don't have time to prove it, of course, but let me just explain what.
Only one point. So you're assuming the extension.
What? Yeah, is the difference.
This is one of the main points in.
Yeah, but from the point of view, yeah, I agree. That's why I don't want to call it sorry, maybe but I just want to say that from the point of view of the discussion nowadays, or whether there are non-invertible symmetries in higher dimensions or not, in a way, it's kind of where you start in the Jones ladder. If you want, where you start in the Jones ladder, whether it's in the observables or in the field algebra, it's unphysical. I mean, and the important point is what is the relation, and the relation is a group. But yeah, it's not really a derivation. It's kind of a complementary derivation. But let me say that it's completely different. It's interesting because, now that you take the question to so if you remember the DHR, they have the algebra of observables, and then they prove that the DHR category is symmetric, and then from that they need to define the dimensions, and they need to prove that the dimensions are integers, and it's kind of a difficult endeavor. And here this is a completely new proof of integrality of the dimensions in higher dimensions.
DHR applies to compact group as well.
Yeah. Here I am assuming finite index. Yeah, just for that part.
You assume that the mu index of B is 1, correct?
The mu index of B is 1. It's a complete theory, and it's only for finite groups. Yeah, correct. Yeah, but in principle, I think, I don't know, maybe it can be extended or not. Yeah.
Take your theorem otherwise.
Okay. Right. No, the theorem is that now we can generalize this. So this is generalization. Let me just, so the idea, let me explain the idea. The idea, we start with a net. This net might have duality violations in balls, in 2 balls, in rings. It might be very complicated. So the first idea is to extend DHR to another net, which is the extension. Okay, this has mu a non-trivial. This has mu a tilde equal to 1. But now this net, we have cured these duality violations, but we have still not. This net still has duality violations, probably in rings or in other type of topologies. And now what we do is to build a dimensionally reduced net. So let me call it A reduce. Okay, by so basically, for example, if we have a loop. I cut here, okay, in the directions transverse to the loop, and I define the algebra so I define an algebra in this dimensionally reduced space that is defined. So in this ball, now this is a ball in the dimensionally reduced space. I define the algebra of the ball to be equal to the algebra of the complete theory in an appropriate ring. Okay, it's just a definition. I mean, it's arbitrary, so there's no naturality here, just mathematical. So this is the algebra of the ring of the So this is the A of the ring associated to that ball. Okay, and now the whole game is to prove that First to prove that the assumptions extend from here to here, that the assumptions extend from here to here, and then we can apply DHR to the reduced net, and so we conclude that these inclusions are given by representations of groups. But the nice thing is that now for higher form symmetries, I can apply that to this and to the complement region. And then I get that I have representations on one region and representations in the opposite, or if you want, group in one region and group in the other. And the only possibility is that this is an abelian group. Okay. Sorry, I was very fast here. And this explains confinement order parameters, the nature of confinement order parameters. And with this, I finish. Sorry.
No,